Hey everyone, it's Dr. Calkins. Today we're going to do a video over week 2. First we're going to do some introductory ideas and then get into the nuts and bolts of the atom. One of the things that we want to focus on in this chapter is learning how to do percentages, learning how to do law of conservation of math problems first. Then we'll get into a history lesson, eventually talk about isotopes, and then furthermore get ourselves into parts of the periodic table. Big chapter, so it'll take quite a few videos to tackle all of those ideas. You may remember from our previous videos that the idea of an atom is pretty old. Around 400 BC, Democritus came up with the idea. 100 years later, Aristotle made it famous, and because he was so famous, for about 2,000 years, it kind of stood on its head and didn't really progress in any great direction. Around the 1600s, with scientific method, things started picking up. And that was thanks to Robert Boyle in particular from our previous videos. Eventually, by the 1800s, John Dalton put a lot of these ideas together. And that's really what we're going to start off and talk about in this introduction of Chapter 2. One of the topics that John Dalton took from was the law of conservation of matter. Law of conservation of matter just really says that the amount of matter you start with is the amount of matter you end with in a chemical reaction. That's different from nuclear reactions in our week 4 videos coming up, but that's going to be in a separate exam as well. So Antoine Lavoisier, a very prominent French chemist of the time, nicknamed the father of modern chemistry, but eventually died in the French Revolution by guillotine, gave us a lot of ideas and a lot of experiments that showed us that mass is always conserved. It's not created or destroyed in a chemical reaction. So if you can imagine some generic example of A and B combined to make C, you'll notice very quickly that if you have 2 grams of A, 3 grams of C, you're going to equal 5 grams of C product. So A plus B gives you C. So really this arrow is just your equal sign, and you're just adding and subtracting. What they could do in addition to a problem like this is say if we have, say, 10 grams of C, we used 6 grams of A, how many grams of B did we use to make it? In a situation like that, we just take 10 minus 6 and realize that that question mark has to be 4 grams in order to equal 10 grams total. So just be aware that these are addition subtraction problems. They're not meant to be difficult. They're just meant to realize that the amount of matter you start with is the amount of matter you end with. Another scientist that John Dalton borrowed some ideas from was Joseph Proust, another French chemist of about the same time period. His idea was based on percentages, and if you remember from math class, percentages are based on this idea of piece divided by the whole times 100. So when you do a piece divided by the whole kind of problem like this, what we're looking for is recognizing the small numbers from the big numbers, recognizing who's a piece, who's a whole, and when to divide by them. So the main idea behind this law of composition, or definite composition as some books call it, the law of proportions basically, is that the percentage of any atom in any compound is going to be the same if it's the same compound. So not meant to be, again, a difficult concept. Really just meaning that you can recognize that compounds are the same if their percentages are the same. So recognize in this situation what we have is 50 grams of water. If we have 50 grams of water, what we need to recognize with that water is it represents the whole compound. So because it represents the whole compound, that's the number that's going to go on the bottom in the denominator. What they list next is decomposed into its elements. So in this case, we have 5.6 grams. Here's our piece. This happens to be our hydrogen piece. And then down here, it gives us our 4.4 grams of oxygen. That's, again, our oxygen piece. So once you recognize those kinds of numbers, then we can divide them a little bit easier. So notice what they did here is they took the oxygen piece, put it on top, took the water piece, in this case pieces, together as a whole. That's basically your 44 plus your 5.6. That's going to equal. So that's going to equal our 50. So notice 50 is basically just 44.4 and 5.6 added together as the whole. Once you divide those times by 100, you get 88.8%. That also tells us that if we add in our other, say, 11.2%, that would be of hydrogen. And together, that would make water. So this basically says that anywhere on the planet, water is going to have 88.8% oxygen, 11.2% roughly hydrogen. And if it doesn't match those percentages, it's not water. So that's what that law of definite composition really says. So John Dalton's theory takes all these ideas for granted. So in number 1, it says all matter is made up of atoms. That's basically Democritus. Atoms cannot be created nor destroyed. That was basically Antoine Lavoisier's law of conservation of matter. Atoms of a particular element are alike. Atoms of different elements are different. That's basically the law of definite composition. That's that percentage-based idea. And then a chemical reaction involves the union and separation of individual atoms. That's, again, kind of relating back to the law of conservation of mass, where things that you start with equal things that you end with in the same amount of mass. This is probably where we're going to stop with this video as an introduction. We're going to take off from here with the history lesson of how this theory was later developed.